Okay, very good morning to all of you, and there I am, the pleasure to address your faculty development program. I will be giving a talk on history of science. That history of science. First, let us understand why we should study history. History is all about past, what happened in the past. Although a firm grasp on the past does not guarantee avoidance of failures and mistakes, understanding the past and its pattern enhances one's ability to analyze the present and the future. So by understanding the past, we are able to analyze the present and to some extent predict the future. Few human activities are devoid of historical analysis. Doctors cannot make a good diagnosis without first taking a medical history. As soon as you go to the doctor, he says, bring your medical history. Then only he starts his diagnosis. A sports coach cannot develop a game plan without analyzing the tendencies, how the player played in the past, and then devise strategies for their opponents. Judges and lawyers cannot draft a judgment or write a brief without grasping the precedent. They ask for case history. A CEO of a company cannot reposition the company without understanding market and sales history. Banks cannot loan to borrowers without taking credit history, and college admission officers cannot make a decision on application until they feel comfortable that a student past academic performance. Academic performance history predicts the trajectory of good future performance. The study of history is indeed worthwhile and necessary for the education and effective citizen and worthy human beings. Historical knowledge is no more and no less than carefully, critically constructed collective memory. As such, it can both make us wiser in our public choices and more richly human in our private life. History is also a bridge to other disciplines. In order to understand humanities and sciences, one needs an historical overview. That's what I'm planning to do today. Writers, artists, scientists, politicians, and everyday people all are conditioned by the historical milieu in which they live. Historical knowledge is a prerequisite for understanding the world in which we live. Magister Vitae means teacher of life. Historia Magistar Vitae, which means history is the teacher of life. Magister Vitae is teacher of life. Historia Magister Vitae is history is the teacher of life. History prepares us to live more humanly in the present and to meet the challenges of the future because it provides us with understanding of the human condition. History is the means of disseminating and comprehending the wisdom and folly of our forebears, our ancestors. Why know about history of science? That's our topic today. Why know about history of science? Remember, change is the only constant in life. Change brings opportunity. Discoveries bring in change. Change brings in discovery. To be successful in life, one must study change. Science is filled with discovery. So to study change, one must study history. Science is filled with discovery. So to study change, one must study history. So today let us see the history of physics, chemistry, mathematics, biology, and economics. For those of you who think economics is not a science, remember, today it is a science and many universities are offering the degree as BSc and MSc economics only, not BA and MA economics. So that's about a brief introduction. Let's see. Everyone is happy to sing the song. ये क्या हुआ, कैसे हुआ, कब हुआ, क्यों हुआ, जब हुआ, तब हुआ, वो छोड़ो, ये ना सोचो. This is what everybody thinks. But historians see it differently. ये हुआ, not ये क्या हुआ. ये हुआ, कैसे हुआ नहीं, ऐसे हुआ. कब हुआ, हिस्टोरियन से इस वक्त हुआ. क्यों हुआ, हिस्टोरियन से इसीलिए हुआ. जब हुआ तब हुआ. डोंट फॉरगेट, याद करो, ये न भूलो. ये हुआ, ऐसे हुआ, इस वक्त हुआ, इसीलिए हुआ. जब हुआ तब हुआ. याद करो, ये न भूलो. That's what is the start for our today's discussion on history of science. First, let's start with history of physics. So, you know why physics? Because everyone says science means PCM, physics, chemistry, math. So I thought we will also go in the same order: physics, chemistry, math, biology, and then last, the surprise, economics. History of physics. History of physics actually spans over 2,500 years, evolving from ancient philosophy into a rigorous mathematical science. It transitioned from classical mechanics, which explained the natural world as a predictable clockwork mechanism, to modern physics, which revolutionized our understanding of space, time, and the subatomic realm through quantum mechanics and relativity. That's the brief ancient foundation. The origin of physics dates back to antiquity, time unknown, time immemorial, where it began as a natural philosophy. This is the answer to, they thought that ऐसे ही हो रहा है, यही होगा, natural philosophy. Early scholars sought to explain the universe using logic and rational observation rather than pure mythology. Ancient Greece, thinkers like Thales of Miletus pioneered the idea that events have natural causes. So if some effect has taken place, there must be a cause to it. So that is how it started, cause and effect study. Then the great philosopher Aristotle developed a comprehensive, though eventually it was found flawed, but he gave a good start with his framework of motion, how movement takes place. And Archimedes, you all remember the fellow who took bath in a bathtub and water fell from the top and he shouted, Eureka! Right? Archimedes made foundational discoveries in hydrostatics and mechanics. Early Eastern and Islamic contributions. Scholars in ancient India, such as Maharishi Kannada's early theories of atomism, and China, Shenkuo's advancement in magnetism and optics made significant leaps. Later, the Islamic world, that the Arabs preserved and vastly expanded on these classical texts with pioneers like Ibn al-Haytham, who revolutionized optics. Then comes the scientific revolution, 16th and 17th century. This period marked the birth of modern physics, shifting the study of nature away from ancient dogma and into the realm of controlled experiments and mathematical formulations. First name that comes into mind is Nicholas Copernicus. Copernicus proposed the heliocentric, sun-centered model of the solar system, challenging the prevailing geocentric view. Remember, old time people thought Earth is the center of everything and all other things, even the sun is going around the Earth. That is the geocentric view. And Nicholas Copernicus said that no, it is heliocentric. The sun is at the center and all planets and moon, etc., they are all going around. Sun is at the center. This is the first beginning, Nicholas Copernicus. Then comes Galileo Galilei, often called the father of modern physics. He famously utilized a telescope for astronomy to study the sky, stars, planets, and proved through an experiment that objects fall in the same rate regardless of mass. He went to the top of the uh, Tower of Pisa and dropped a heavy object and a lighter object to a tube, and both fell down at the same time. Everybody thinks heavier must fall fast, the lighter one will take time. It's not correct. The gravity is the same. Right? Experiment that objects fall at the same rate regardless of mass. Then comes Isaac Newton, the man for whom the apple fell. Right? He published Principia Mathematica, unifying Galileo's kinematic and another great physicist, Kepler's planetary laws, where he put all the planets, etc., in place into the three laws of motion, the famous three laws of Newton, right? And the law of universal gravitation, effectively creating classical mechanics, right? So that is about Isaac Newton. That classical physics, 18th and 19th century, during the Enlightenment and the Industrial Revolution, physics applied and expanded upon the Newtonian mechanics, organizing their understanding into distinct fields. Then came thermodynamics, the study of heat, energy, and work, which led to the formulation of laws of thermodynamics and the concept of entropy. Remember, today you have so many branches of engineering, this, that, and all. No phenomena can violate the laws of thermodynamics. You cannot design a system which violates the law of thermodynamics. That is the beauty of this. Then comes electromagnetism. Scientists like Hans Christian Ørsted, Henry Mary Ampere, and Michael Faraday discovered the relationship between electricity and magnetism. Then comes the most famous man, James Clerk Maxwell. He synthesized the discoveries, electricity, magnetism, etc., into a single set of equations called the Maxwell equation, which unified electricity, magnetism, and light into a single electromagnetic wave theory. Right? So Maxwell's equation brings the electricity, magnetism, and light into a single electromagnetic wave theory. Then comes modern physics. That is the 20th century till now. At the turn of the 20th century, phenomena such as what is radioactivity, Marie Curie, remember radioactivity, and the photoelectric effect could no longer be explained by classical physics, forcing a radical paradigm shift. So classical physics was talking about motion, Maxwell's laws and all those things, but that could not explain what is radioactivity and photoelectric effect. And then comes the modern physics. Classical mechanics now moves into modern physics. First comes the theory of relativity, and Albert Einstein introduced a special relativity, establishing that space and time are linked. The famous equation E is equal to mc square, and later general relativity, which redefined gravity as the geometric curvature of space-time. That's about Albert Einstein. Then comes quantum mechanics. Pioneer scientists, physicists, pioneers like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, they discovered that energy exists in discrete quanta, not continuous, but pockets, quanta, and developed a probabilistic framework to explain matter at atomic and subatomic scale. Then comes contemporary physics, physics of today. Today, physics utilize the standard model. I will explain you what is the standard model. To describe, is everyone able to see the slides?
Yes.
Is everyone able to see the slides?
Yeah, yes, we can see.
Okay. Contemporary physics. Today, physics utilize the standard model. Standard model. What is it? I'll explain you. To describe fundamental particles and forces, while modern research centers on bridging the gap between quantum mechanics and general relativity. You have new physics theories called string theory, quantum computing, and investigating dark matter and dark energy. So let me explain what is the standard model. Remember, we all think matter is made up of atoms. There is a nucleus, proton, electron, neutron, electron. That's it. But the standard model tells that matter has certain particles which are called fermion. The standard model talks of particles also known as fermion, which is made up of quarks and leptons. Right. The quarks is the one which gives rise to your protons and neutrons, and leptons. That is what is your electron and other things. Right. So they said the matter has got 17 particles, 12 under particles, and 5 under force carriers, which are also called bosons. Right. So you have fermion, which includes quarks and lepton, and force carriers, also known as bosons. That is the standard model which describes matter. Now, what is this investigating dark matter and dark energy? See, we don't know how the universe came. Our Rigveda sloka says that सृष्टि के पहले कोई सच नहीं था, असत्य भी नहीं था, आकाश भी नहीं था, अंतरिक्ष भी नहीं था. Then what is it? So scientists believe there's something called dark matter and dark energy present in the universe. So the dark matter is what which is leading to the holding of different universes in place, different galaxies in place, so that we don't collide and lead to a catastrophe. So dark matter, we are calling it dark matter because it exists, but our telescope and our other equipment cannot see. Dark energy. There is also energy which is what is making the universe expand. The universe is continuing to grow. More and more galaxies are getting added. So physics is really a fantastic field, moving in a great way. Now let's go to history of chemistry. History of chemistry. Chemistry evolved from practical ancient art like metallurgy and perfume making into a rigorous modern science. It transitioned through mystic proto-science of alchemy to establish the atomic theory, the periodic table, and also quantum mechanics. Remember, quantum mechanics has some physics aspect and some chemistry aspect. Remember, we always study history of civilization as Stone Age, Bronze Age, Iron Age, right there. Bronze Age, Iron Age, all involved metallurgy and chemistry, right? Bronze Age and Iron Age is all dealing with metallurgy, and that is about chemistry. Now let's see the ancient origin and alchemy. 4000 BCE, before Common Era, and 1600 CE, Common Era. Early chemistry was driven by practical needs rather than theoretical understanding. We want something, so let's somehow make it. But don't bother about what is the theory and mechanism behind it. First, early metallurgy and craft. Civilization developed foundational technologies, how to extract metal from a ore, iron ore, say iron, making glass from sand, how to make glass, fermenting wine, and producing soap. These are all the starting things. Then comes Taputi Bella Decale, the Babylonian female perfumer recorded in 1200 BCE in clay tablet, is widely considered the world's first recorded chemist. Right? Made perfume from flowers and leaves, how to get perfume. Taputi Bella Decale. Then comes alchemy. Alchemy is the old name for chemistry, sort of Jugaad chemistry, let's say. And it flourished in China, the Islamic world, and Europe. And alchemists thought everyone wanted gold is a very valuable metal. How to convert other material? How to convert iron into gold? So alchemy was working on a formula by which gold can be made from anything. So to turn base metals into gold. That is what was alchemy. But during this trial and error, they accidentally invented distillation apparatuses and discovered elements like phosphorus. Right? Sugar. Then comes birth of modern chemistry, 17th and 18th century. The field shifted from recipe-based practice to an experimental science. First comes the man, Robert Boyle. Boyle's law, you all remember. 1647 to 1691. He shifted chemistry away from alchemy by defining elements and pioneering the relationship between gas, pressure, and volume. PV is equal to nRT, the ideal gas law. That Robert Boyle, he also had another Charles, who made Charles law. Combination of Boyle's law and Charles law led to the ideal gas law, PV is equal to nRT. Then comes the next great chemist, Antoine Lavoisier, 1743 to 1794, from France. He is regarded as the father of modern chemistry. He disproved the phlogiston theory. This is interesting. Phlogiston theory, and explained combustion and oxidation, and formulated the law of conservation of mass. Right. Phlogiston theory. See, when something burned, it led to ash. Everybody says that all matter contains something called phlogiston, which is what is resulting in the formation of ash. Phlogiston. Something they did not know, so they gave a name. All matter contains the phlogiston, which when burnt forms the ash. But Lavoisier said that air has oxygen and nitrogen, and explained combustion as a reaction of matter with oxygen, that is oxidation, and formulated the law of conservation of mass. And Lavoisier. Now comes the quantitative theory of the atomic age, 19th century. The 1800s introduced mathematical rigor on foundational building blocks of matter. Comes John Dalton, 1766 to 1844. He proposed the modern atomic theory that all matter is made up of atoms, molecules, stated that all matter is composed of indivisible, indestructible atoms. That is the smallest matter. So it is atoms which make up matter. That is John Dalton. Then comes Dmitri Mendeleev, 1834 to 1907. He published the first recognizable periodic table in 1869. Remember, it is valid even today. Nobody has been able to change the periodic table. It was so perfectly made, organized the elements by their masses, and Mendeleev also predicted undiscovered elements. There will be someday a new element with this atomic number and mass. So he built the periodic table, Dmitri Mendeleev. Now comes quantum mechanics, the chemistry part of it, and modern specialization. 20th century till present, the understanding of the atom deepened, and the discipline I already told. He said that the atom has now proton, electron, neutron, fermion, boson, all things are coming up. Right. Subatomic particles. Discovery of the electron. A.J. Thomson, 1897. Then comes nucleus. Ernest Rutherford, 1911. And quantum models of electron orbital redefine atomic structure. The atomic structure now talked about nucleus and the electron orbital. Then comes major milestone, innovations such as Haber-Bosch process for synthesizing ammonia. Remember, all plants require nitrogen as a major nutrient for plant growth. All plants. But all plants are not capable of taking atmospheric nitrogen. Only leguminous plants, dal, vagera, can capture the atmospheric nitrogen. But what about other plants? They require nitrogen, and nitrogen is there in the air, but it is difficult to extract the nitrogen from the air. Haber-Bosch came with the set of reactions for synthesizing ammonia, right, by which hydrogen and nitrogen will react to form ammonia, right, using an iron catalyst, and that is how fertilizer is being made today, and the green revolution, and we all have enough food to eat. The development of synthetic polymers, that is plastics, fibers, elastomers, right. So this reshaped the global industry. Now modern focus is on green chemistry, nanochemistry, computational chemistry using artificial intelligence, metal organic frameworks, etc. That's about a brief on the history of chemistry. Now let's go to history of mathematics. History of mathematics, very interesting. The history of mathematics goes back over 30,000 years. 30,000 years, evolving from prehistoric tallying into today's complex science. It spans ancient foundational discoveries in Mesopotamia. Mesopotamia is present-day Iraq, where the famous rivers Tigris and Euphrates flow, and where civilization, ancient civilization started, followed by Nile Valley civilization and the Indus Valley civilization and the Yellow River civilization, etc. So, these discoveries in Mesopotamia and Egypt, the Greek revolution of deductive proof, how to deduce the proof for a phenomenon, pivotal advancements in India and the Islamic golden age, modern calculus and abstract era. Let's look at what happened in prehistoric and ancient foundations. 35,000 BCE, before Common Era, early humans used tally marks on boards. Right? On board, they used to make a mark and say, this is some length, 2 board length, 3 board length, like that. The Lebombo board, that is a historic happening, to track time and quantity. Right? 3000 BC, Sumerians in Mesopotamia developed a sophisticated base 60 counting system. Remember, today we talk 1 hour has got 60 minutes and every minute has got 60 seconds. These were all developed by the Sumerians in Mesopotamia 3000 BCE. It still influences how we measure time and circles. Right? 1800 BCE, Babylonians used clay tablets to record Pythagorean triples and solve quadratic equation. Ax square plus bx plus c is equal to 0. So x minus b plus a minus square root of b square minus 4a by 2a. Right. 1800 BCE, Babylonians wrote it on clay tablet. 1650 BCE, the ring mathematical papyrus. Papyrus is a paper that demonstrates the Egyptians' ability to calculate geometrical areas, area of a triangle, rectangle, square, etc., volume of different shapes, and fraction. Right? These all happened. Then come classical Greece and early India. 540 BCE, Pythagoras found the Pythagorean school and proved that the foundational geometry theorem, right? So that's about Pythagoras, a famous mathematician. 300 BCE, Euclid, right? Element establishing geometry on a rigid system of axioms, postulates, and proofs. Axioms are those which we accept without any proof. ले लेते, मान लेते, no proof, ऐसे ही होगा, like that. 250 BCE, Archimedes uses the method of exhaustion to calculate areas and volume. Remember, Archimedes contributed to physics as well as to math. Method of exhaustion to calculate areas and volume, closely approximating the value of pi, that is 22 by 7, right? So the famous number 22 by 7, and he gave how to approximate it. Then 300 to 500 common error. Indian mathematician developed the positional based 10 decimal system, the concept of zero, right? So somebody gets 0 marks in the test, actually says that Indian discovered zero, right? Revolutionizing calculation. Okay, that's about mathematics there. Then comes the Islamic Golden Age, 820 CE. Persian mathematician Muhammad ibn Musa al-Khwarizmi, right? Al-Jabbar, laying the foundational groundwork for modern algebra. Remember, modern algebra came from the Islamic Persian mathematician. Then come 1000 to 1200 common era scholars like Al-Biruni and Omar Khayyam, significantly advanced trigonometry, also triangle, rectangle, trigonometry, sine, cos, tan, and the geometric solutions of cubic equations. Right. Renaissance and the 17th century. 1200 CE, Fibonacci introduced the Hindu-Arabic numerals to Europe through his book Liber Abaci. Pierre de Fermat, 1601 to 1665. He was a French mathematician. Basically, he was a lawyer. He is regarded widely as one of the greatest mathematical minds of the 17th century. He is best known for his pioneering work in number theory, calculus, and probability. Then come 1614. Lord Napier, he introduced algorithms, drastically simplifying complex multiplication and division. See, today we have calculators and all those things, but those days, math, multiplication and division, they're done using logarithm, anti-logarithm, etc. John Napier, 1614, introduced it. 1637, Rene Descartes publishes Law Geometrica, inventing analytical geometry and linking algebra with geometry. Then come 1684 to 1687 CE, Gottfried Wilhelm Leibniz and Isaac Newton. Isaac Newton did a lot of things in physics and also in maths also. Independently published papers inventing calculus. Leibniz and Newton are the people who brought in calculus, differentiation, integration, and all those things, describing rate of continuous change. Now comes mathematics in 18th and 19th century. 1736, Leonhard Euler solved the Königsberg bridge problem, indirectly giving birth to graph theory and topology. Königsberg bridge problem, very interesting. There is a river in Russia, Königsberg, and it has 7 bridges. And different parts of the city across the river, there were 7 bridges, and a puzzle was somebody should go through all the 7 bridges without backtracking in any one of them. So that is what Euler solved and gave birth to what is called today as graph theory and topology. 1799 CE, Carl Friedrich Gauss proves the fundamental theorem of algebra. 1858 CE, August Ferdinand Mobius invent the Mobius strip, paving the way for topology. Mobius strip is a very interesting thing where you fold a paper like a circle with a twist there. It is there in many fancy parks, etc. Mobius strip that gave rise to topology. 1874 CE, George Cantor proved that there are different mathematical cycles of infinity, establishing set theory. Now today let's come to modern maths and computing. 1900 CE, David Hilbert presents a famous list of 23 unsolved mathematical problems at the International Congress of Mathematicians shaping 20th century research. David Hilbert, 1931 CE, Kurt Gödel publishes his incompleteness theorem, proving that formal mathematical systems will always contain unprovable statements. Everything cannot be proved mathematically. There will be always some unprovable statement. 1936 CE, Alan Turing formalizes the concept of algorithm and the Turing machine, laying the theoretical foundation for what we call today as computer science. 1936 CE, Alan Turing. 1995 CE, Andrew Wiles publishes the finalized proof for Fermat's law theorem. Fermat was another great mathematician and he solved a 350-year-old mathematical puzzle. I think Fermat wrote a to the power n plus b to the power n is equal to c to the power n is true only for number 2 and not for anything else. A to the power n plus b to the power n is equal to c to the power n is valid only for 2, and that's something what Fermat last theorem was. It was finally proved in 1995. Fermat wrote it several years back. Now, year 2000 to present, ongoing development, future, high-profile breakthroughs in combinatorics such as Green-Tau theorem, chaos theory, expanding intersection of mathematics with machine learning, deep learning, artificial intelligence, maths is on and on and on. Now come to the history of biology. TCM is over. Let's bring the TCMB, biology. History of biology. History of biology spans from ancient philosophical observation to modern molecular genetics. It is a chronological story of how humanity mapped the building blocks of life, classified species, and discovered the universal mechanism of evolution and inheritance. Let's see the macro observation, world and time, antiquity and Renaissance. 350 BCE, Aristotle, great philosopher, he lays the groundwork for by categorizing living things based on their traits and behavior. He classifies them into various groups. 1543, Andrew Bezalis publishes the first comprehensive human anatomy text, revolutionizing medicine through direct dissection. Surgery has started. 17th and 18th century, microscopy and taxonomy. Right. 1665, Robert Hooke examined a corpse under primitive microscope and coined the term cell. Right. 1674, Anton von Leeuwenhoek discovers microscopic life observing bacteria, protozoa. 1735, Carl Linnaeus publishes Systema Natura, establishing modern system for classifying organisms into a hierarchy, order of classification. Then comes 19th century, evolution and heredity. 1838, Matthias Sheldon and Theodor Schwab proposes the cell theory, established that all living things are composed of cells. Remember, the chemist talked about all matter made up of atom made up of proton, neutron, electron, and all those things. Now, similarly, the biology people said all living things are composed of cells. And 1859, Charles Darwin publishes on the origin of species, survival of the fittest, introducing the theory of evolution by natural selection, Darwin's law. Then comes 1866, Gregor Mendel publishes the foundational laws of Mendelian inheritance after tracking traits in pea plants. Right. So he said that how genetic the gene moves from generation to generation. Now the 20th and 21st century, that comes to the area of molecular and modern biology. 1953, James Watson and Francis Crick. Watson-Crick model, they determine the structure of DNA as a double helix structure, creating the bedrock for modern genetics. Watson-Crick model, double helix structure of 1990 to 2003, the Human Genome Project successfully mapped the entire human DNA sequence. Then comes the genomics era, 2000 to 2005. In 2001, draft sequences of the human genome are published by the Human Genome Project and Cellular Genomics. 2002, rice becomes the first crop to have its genome fully decoded. 2003, the Human Genome Project is completed, successfully mapping all human genes. Then comes the era of synthetic biology and stem cells, 2006 to 2010. 2006, scientists successfully create induced pluripotent stem cells, iPSCs, induced pluripotent stem cells from differentiated cells, drastically changing regenerative medicine. Today, you see, stem cell therapy has come to 2000. These biologists worked on it. 2007, next generation sequencing called the FDP commercialization. This radically accelerates functional genomic studies and lowers the cost of sequencing per base pair. Right? When the genes are all in pairs, right? How to sequence it. 2010, J. Craig Venter Institute creates the first synthetic bacterial cell controlled entirely by a chemically synthesized genome. Major breakthrough. The gene editing revolution. Like you give a kabada to a tailor who will cut it in different ways and make the fancy cloth dress you want. Gene editing. Biologists have found methods of editing the gene. Gene editing revolution. 2012 to 2020. 2012. Jennifer Doudna and Emmanuel Charpentier published their landmark discovery of CRISPR-Cas9, turning it into a programmable, highly precise DNA editing tool. 2019, CRISPR is first formally utilized in human trials for cancer treatment. Now, 2020 onwards, it is the artificial integration and advanced therapeutic, like 2020 to present. 2020, the rapid development of mRNA vaccine. Remember, the corona vaccine and the mRNA vaccine drastically alter the timeline of pandemic response and modern vaccinology. 2021, DeepMind AlphaFold revolutionizes structural biology by accurately predicting the 3D structure of nearly all known proteins. Right? 2023, the US FDA approved the first cell-based CRISPR therapy, Casgevy, to treat severe sickle cell disease. This is the blood cancer type, sickle cell disease. 2026, advanced clinical trials and commercial rollout of in vivo gene editing therapeutics and personalized mRNA cancer vaccine dominates life science pipeline. Tomorrow, the doctors will be more biologists than they are only doctors. So, we are moving now into the history of economics. History of economics, that's a very interesting picture. The history of economic thought evolved from early philosophical moralizing into the rigorous data-driven social science of today. Major eras, foundational texts and theories shifted in direct response to prevailing societal challenges of industrial revolution, global depression, and technological advancement. Ancient and pre-classical thought, antiquity to 18th century. 1750, the Code of Hammurabi produces like our Manusmriti, that is the Code of Hammurabi introduced the early economic framework, standardizing norms for commerce, wages, and business ethics. 350 BCE, Aristotle. Remember, Aristotle did work in physics, in math, and also in economics. Right? Aristotle analyzes the wealth in politics, concluding that private property is beneficial, but accumulation of wealth for its own sake is unnatural. Right? So you can have property, but keep on accumulating wealth for own sake is unnatural. That is Aristotle. And 321 to 300 BCE, Arthashastra by our own Chanakya on statecraft, politics, economic policy, and military strategy. 14th century, 1332 to 1406, Arab scholar Ibn Khaldun explores the division of labor, profit motive, the rise and fall of empires in Al-Muqaddimah. 16th and 18th century, mercantilism dominates, that is business, merchant. Nations measure wealth by accumulation of gold and silver, promoting heavy state intervention and trade protectionism. Let's see the parts of classical physics. The birth of classical economics, 18th to 19th century, 1776. Adam Smith, first name comes, Adam Smith publishes The Wealth of Nations, widely considered as the foundation of modern economy. Smith introduces free market concept of invisible hand and the benefits of division of labor. Adam Smith, right? So he laid the foundations of modern economics. Then comes the 1870, David Ricardo publishes Principles of Political Economy and Taxation, expanding on Smith's work and formulating the influential theory of comparative advantage in international trade. Then comes 1848, that is John Stuart Mill publishes Principles of Political Economy, bridging classical economics with social philosophy and utilitarianism. Then comes the communists, Marxism and the reaction to capitalism. 1867, Karl Marx, German, publishes the first volume of Das Kapital, critiquing capitalism. Marx argues that system exploits the working class, that is, the capitalism exploits the working class, and predicts its eventual replacement by a classless communist society. Then comes the neoclassical revolution, that is late 19th to early 20th century, 1870, the marginal revolution led by Karl Menger, William Stanley Gibbon, and Leon Walras. They introduced the concept of marginal utility. Economics began using heavy mathematical models to explain how consumers make decisions based on satisfaction. 1890, Alfred Marshall publishes Principles of Economics, officially establishing the neoclassical school by combining supply, demand, marginal utility, and the cost of production into a unified framework. We start hearing about law of diminishing returns, etc. The rise of macroeconomics, that is 1930s, 1936, John Maynard Keynes publishes the general theory of employment, interest, and money. This marks the birth of Keynesian economics, arguing that government must actively intervene using fiscal policy during economic downturn and depression rather than waiting for market to do self-correction. Don't wait for market to do self-correction. Government should intervene with the appropriate policy to correct. Monetarism and neoliberalism. That's late 20th century, 1970s, stagflation causes decline in classical Keynesian policy, and Bank, that is the Reserve Bank said, should focus on controlling the money supply to manage inflation. 1980, neoliberalism influences global policy favoring deregulation, free trade, and privatization. Contemporary economics, 1990s to present, 2018. The global financial crisis sparked the resurgence of Keynesian ideas and sparked new research into systemic risk, economic inequality, and the limits of purely self-correcting market. Right. So market cannot do self-correction. Government should come with a fiscal policy to correct the downturn in the economy. That's what is the global financial crisis thought. 2000 to 2026, modern economics expand via fields like behavioral economics, incorporating psychology into economic model, the widespread use of big data and randomized control trials to analyze policy outcomes. So economics has taken in a big way to the history of science. So that's about history of science. Thank you all. But all that I would like to say is, see about history of each topic, physics, chemistry, math, biology, economics. I have spent just about 10 minutes. The concerned physics, chemistry, biology, math teacher can expand this 10 minutes into at least 1 hour and make students appreciate each of them. There are a lot of YouTube available showing the history of math, physics, chemistry, biology, economics, etc. They can be played to the students so that it will be a good learning experience both for the school teachers as well as for the students. Okay, so thank you all. Thank you.
Thank you, sir. You are able to hear us? Hello.
Yeah, we are hearing.
Thank you. And I am sure that my CEO teachers will make use of this session. And as you suggested, through YouTube, the respective teachers of math, science, math, physics, chemistry, biology, and economics will explore more on this to the students. Thank you, sir, and thank you all to all the teachers who are present here.
I have already. Yeah, thank you all. Thank you.
Yeah, we have learning from.
I am thankful to Yamuna Mishra Academy for giving me this opportunity and giving me just 1 minute, please. And yeah, just thank you all. Thank you for the memento given to me. I appreciate it sincerely. I appreciate it sincerely. Thank you. Thank you.
Thank you. Thank you.
Okay.
And all of you, before going for a break,
Okay.